So my name is Vishnu, a PhD student at McGill University. I'm going to be presenting our work, Online Coloring and a New Type of Adversary for Online Graph Problems. This is joint work with Yachia Lee and Dennis Pankratov. I'll start with an introduction to online graph problems. So in an online graph problem, the input is revealed one item at a time, so one vertex or one edge at a time. And the algorithm must make an irrevocable decision after observing each item. We'll be looking at the vertex arrival model, where the graph is revealed one vertex at a time. So at time step t, the vertex v, which is sigma of v for some permutation sigma, arrives, and we learn the pre-neighborhood of v. So we learn the adjacency status of v to all of the vertices that have arrived before v. Let's look at an example of this. In this graph, there are 5 vertices, 6 edges, and the vertex labels indicate the arrival order. So we can rearrange them on a line according to the order. And in the first time step, vertex 1 arrives. In the second time step, vertex 2 arrives, along with the edge 1, 2. We don't see the edges 1, 3, and 2, 3 yet, for example. In the third time step, the vertex 3 and the edges 1, 3, 2, 3 arrive, and so on. So since we need to make an irrevocable decision each time step, some examples of online graph problems include the coloring, matching, independent set problem, and so on. In this talk, we'll be focusing on the coloring problem, but the model we introduce has broader applications to other problems in online graph theory. All right. So in the online coloring problem, the input is a graph G with vertex at v1 to vn, so n vertices, along with the permutation on the vertices, which indicate the arrival order. And the output is a proper coloring c1 to cn, such that vi is colored with ci. So the algorithm needs to assign a color to every vertex, such that we have a proper coloring. So any pair of vertices that are adjacent get different colors. And the goal of the algorithm is to minimize the total number of colors that it uses to color the graph. Let's see an example. So in this graph, there are 4 vertices. So in time step 1, vertex 1 arrives. In time step 2, vertex 2 arrives. And there's no edge between 1 and 2. So 1 and 2 are isolated vertices. Now the algorithm has 2 choices. It can either color 1 and 2 with the same color, or it can color 1 and 2 with different colors. If it colors 1 and 2 with the same color, then suppose vertex 3 arrives and has an edge to 1. Then it needs to color vertex 3 with a different color, and if vertex 4 arrives and has an edge to 3 and 2, again it needs to color vertex 4 with a third color. So the algorithm uses 3 colors, despite this graph being 2 colorable. If instead the algorithm gave vertices 1 and 2 different colors, then if vertex 3 arrives adjacent to both of them, then the algorithm is again forced to use 3 colors. So for every algorithm, there's some instance that the algorithm is not coloring optimally. So we have that even with no computational restrictions, no online algorithm can color optimally. And this is an information theoretic restriction. So what can we do? So what we do is, in the online coloring problem, as a standard for a lot of online problems, we study the competitive ratio of online algorithms. So we denote by A, G, sigma, the number of colors used by algorithm A to color the graph G with ordering sigma. And we say that the competitive ratio of algorithm A for a graph class cal G is the supremum over all graphs in the graph class, so the worst case graph and worst case ordering sigma of AG sigma over chi of G, so the chromatic number of G. Let's look at a quick example. First example we'll see of an online algorithm is first fit. It's widely studied. It's the simplest algorithm. It's essentially the same as the greedy coloring algorithm. So first fit colors the arriving vertex V with the smallest positive integer that is not used for a previous neighborhood of V. So it looks at the neighborhood of V and uses the first integer that's not in that neighborhood. So the first feasible choice for the vertex B. In the same example we had before, first fit colors vertex 1 red, vertex 2 blue, vertex 3 green because it sees both 1 and 2. But it colors vertex 4 red because vertex 4 does not have an edge to vertex 1, and it's the first color that was used. Colors vertex 5 blue since it doesn't have an edge to 2. It's the second color that was used. So first fit can color those 3 colors. In general, it's easy to see that any online coloring algorithm can color any graph with it on n vertices with at most 10 colors. It can just assign a different color to every vertex. But can first fit do significantly better? It turns out the answer is no. First fit has comparative ratio omega of n, even for the very restricted class of bipartite graphs. So if you present a bipartite graph, which is a complete bipartite graph minus a perfect matching, so if you just remove the matching edges 1, 2, 3, 4, 5, 6, and so on, and present them in this order, this is what first fit does. It colors both of these vertices red because they're isolated, colors vertex 3 blue, and vertex 4 blue, colors vertex 5 green because it sees both 2 and 4, colors 6 green because it sees both 1 and 3, and so on. It has to use a new color here. So for every pair of vertices, first fit uses a new color. So it uses n over 2 colors, even though the graph is 2 colorable. So the comparative ratio is omega of n. So the first question that people looked at is whether there exist algorithms that can do better, that actually have sublinear comparative ratio. In their seminal paper in 1989, WAOA, Sachs, and Trotter presented an algorithm that has sublinear comparative ratio. Comparative ratio O of n over log star n. This led to a whole chain of results and improvements until O of n over log n by Halderson in 1997, and also a lot of results for special cases. So instead of producing a general graph, if the adversary is restricted to producing chi-colorable, 4-colorable, 3-colorable graphs, there are truly sublinear comparative ratio algorithms. And interestingly, for bipartite graphs, the original paper of WAOA, Sachs, and Trotter gave an algorithm called CBIP that has logarithmic comparative ratio. This is a well-studied algorithm as well. We'll revisit this later in the talk. There are also lower bounds on the same graph classes, general, bipartite, and chi-colorable. And something interesting that you can notice in this table is if you look at general graphs, the upper bound of n over log n and lower bound of n over log square n is just logarithmically have just logarithmic gap. And if you look at bipartite graphs, the upper bound of log n and the lower bound of omega of log n are essentially tight. But for graphs with small constant chromatic number, like 3 and 4 colorable graphs, the upper bound is still a fairly large polynomial, but the lower bound is just polylog. So there's a huge gap here. So we want to try to understand why there is this gap and where the gap comes from, and how the lower bound techniques work, whether there are any limitations. So all lower bound techniques, nearly all lower bounds for online coloring are obtained through this adversarial strategy, where you present an adversary that's able to observe the algorithm's coloring and adversarially construct the future of the graph, so that for every algorithm, it forces the algorithm to use extra colors. So if you want a lower bound specifically for the class of chi-colorable graphs, then the adversary must keep track of the chromatic number in the background, because it needs to produce a chi-colorable graph, while forcing the algorithm to use more than chi-colors. So we use colors to refer to the colors chosen by the adversary in the background, and bins to refer to the colors chosen by the algorithm. So nearly all of the lower bound techniques for chi-colorable graphs follow this strategy, this common theme. First, the adversary creates a collection of disjoint components and observes the algorithm's choices. Then in at least one component, the adversary chooses a different optimal color. So it just switches the optimal coloring around. And then it presents a new vertex that connects all of the components and merges them together. But this forces the algorithm to put the new vertex in a new bin, because while the adversary only sees 2 different colors, the algorithm sees all 3 bins for this vertex. So if we want to understand what the power and the limitations of this create and merge technique were, and in order to do this, we introduce an extra restriction on the adversary. We call this the kappa component bounded or kappa CB adversary. What we ask is, what happens if we limit the number of components that the adversary can create in any time step to a parameter kappa? This allows us to obtain a finer understanding of the power and limitations of this technique, but it also has much broader application. Because in real-world graphs, in most real-life applications of online graphs, such as computer networks, social networks, public transit networks, etc., arriving vertices attach themselves to existing components. So it turns out that in the online presentation order, there are very few connected components at any point in time. So this does help us to analyze algorithms more usefully in the real-world context. And also, it's an early step towards parameterization for online algorithms. While parameterization is highly successful in the offline world, there's very little systematic approach towards parameterization for online algorithms. So with this parameter kappa, we're trying to change that. So more formally, at any point during the presentation of the graph, the adversary is restricted to using at most kappa connected components. And the number of vertices n, unlike earlier, is not necessarily a parameter. We can include it as a parameter, both n and k, but what we're interested in is if the adversary can produce an arbitrarily large graph. So n is arbitrarily large, but it's restricted in the number of connected components, then what happens? So we define beta of a kappa g as the number of bins the algorithm A uses when a kappa CB adversary constructs the graph G. And beta of A kappa cal G for a graph class cal G as the supremum over all graphs in the graph class of that value. And beta of kappa G, this is like structural property of the graph class, is the infimum over all algorithms, so it's a lower bound over all algorithms, beta of A kappa G. So it's similar to the lower bound on the comparative ratio, except now we're expressing it in terms of kappa instead of as a function of n. So let's see if you're still following me. Just to check your intuition, observe that if we let omega denote the set of all graphs, then beta 1 omega is infinity, because even if the adversary is restricted to one connected component, you can just present the graph Kn, the complete graph of n vertices, where n is arbitrarily large and 4 is arbitrarily many colors. That's because the beta that we define is defined in terms of the absolute number of bins rather than the comparative ratio. For most of the problems we're looking at, the comparative ratio is, the chromatic number of the graph we're producing is small or is constant. So this only differs from the comparative ratio by a constant. That's why we're doing this. It's easier to see it this way. Okay, so here's an overview of the results we have. In terms of upper bounds, we're going to analyze the algorithms first fit and CBIP under the X-CB Adversary. In terms of lower bounds, we have lower bounds for several graph classes: trees, bipartite graphs, three-colorable graphs, planar graphs, tree-decay graphs, etc. So while we have all of these technical results, I want to emphasize that the main contribution of our work as we see it is conceptual rather than technical. We do have a bunch of technical results. So let's start with the upper bounds. Our first theorem is a very simple theorem for the first fit algorithm. Beta first fit kappa tree is kappa plus 1. So on trees, against the kappa component bounded adversary, first fit uses at most kappa plus 1 colors. And in fact, at least kappa plus 1 in the worst case. So suppose first fit uses n plus 1 bins for some m, and consider the first vertex that was placed in bin m plus 1. Then there are necessarily m vertices that are in bins 1, 2, and so on up to m that this vertex v sees. Otherwise, first fit would have used one of those colors. And since the adversary is constructing a tree, these vertices are in distinct components. Otherwise, you create a cycle. So very simple proof. Beta first fit kappa tree is, this shows that beta first fit kappa tree is at most kappa plus 1. We'll get to the lower bound later on. In the full paper, we also completely characterize the performance of first fit on a bunch of graph classes. Against the 1 CB adversary, constructing a bipartite graph, first fit is optimal. So that's kind of clear. Against the 2 CB adversary, first fit uses infinitely many colors. And that's the example we saw from earlier. And against the kappa CB adversary, constructing a chi-colorable graph, first fit uses infinitely many colors for every kappa at least 1 and chi at least 3. And also, a 1 CB adversary can force first fit to use infinitely many colors, giving a triangle-free graph. Okay, so we move on to the second algorithm, which is CBIP. This is also a widely studied algorithm. This was introduced by Lovaas, Sachs, and Trotter in 1989. In this algorithm, when a vertex V arrives, CBIP computes the entire connected component of that vertex, CC of V. And since the input is bipartite, CC of V can be partitioned into vertex sets A and B. So CBIP only applies to bipartite graphs. And then suppose the vertex V is in the A side of the partition, then CBIP colors V with the first color that is not used in the B side of the partition. Let's look at the same worst case example for first fit, but apply CBIP to it. So now CBIP also colors these red, same as first fit. CBIP also colors these blue. But when the fifth vertex arrives, CBIP looks at the entire connected component and the opposite bank, which has red and blue vertices, and colors this green. Now, when the sixth vertex arrives, again, CBIP looks at the entire connected component. On the opposite bank, it sees red, green, and blue. So it has to use a new color. It uses yellow. So at this point, it's used an extra color over first fit. But the advantage of this is that I can continue to color the vertices on the left side green because there's no green on the right side. I can continue to color the right side yellow because there's no yellow on the left side. So first fit, CBIP does a lot better on this worst case example for first fit. In general, they show that CBIP uses at most 2 log n bins, which is really close to the lower bound from Bean, which is that CBIP uses at least log base 2n bins. Interestingly, there's been a lot of work to close just this constant factor 2 gap. In 2012, Bianchi et al. Showed that CBIP uses at least 1.137 log n bins. And in 2014, Gutowski et al. Showed that it used at least 2 log n bins. Now, in order to force 2 log n bins, in Gutowski et al.'s paper, if you analyze what the adversary is doing against CBIP, it uses log n different connected components to force CBIP to use 2 log n bins. And this, we prove that this is a necessary feature of their proof, because interestingly, the comparative ratio of CBIP on bipartite graphs is simply kappa, which is the number of components that the adversary is allowed to use. So we show that beta of CBIP kappa bipartite is 2 kappa. This is really good because in real world graphs which are kappa component bounded, CBIP does really well. For example, if kappa is constant, CBIP actually uses constantly many colors. What's also weird about this is that the lower bound, beta CBIP kappa bipartite, comes from trees. So we have that beta CBIP kappa tree is at least 2 kappa. This is weird because first fit actually outperforms CBIP on trees, even though it's a lot worse on bipartite graphs. It's kind of unintuitive under the X-CB Adversary. Okay, so with that analysis of the two algorithms, let's move on to graph classes. First result is for trees. First fit is not only better than CBIP on trees, it's optimal on trees under the X-CB Adversary. So beta kappa tree is kappa plus 1, so you cannot do better than kappa plus 1. So the lower bound is witnessed by the forest construction due to beam. This is an inductive proof. So suppose kappa is 1 with a single connected component. You can force any algorithm to use two colors, right? Just give it an edge, and it's supposed to use two different colors. Now, with two connected components, if you're constructing a tree, what you can do is present another vertex. So either you're already seeing three different colors here, in which case you're done, or this is going to be the same as this color. But then you have a difference between this vertex color and this vertex's color. So you can present a new vertex and connect it to those two, and that's supposed to use a third color. So now for any algorithm, as long as you're allowed to use two connected components, you can present a tree that uses three colors, so kappa plus 1 colors. And you can just repeat this process now. If you have, if kappa is now 3, you can do this, set this component aside, and then create two more components, and you're going to get, for each connected component, you're going to be able to identify one vertex that has a unique color and connect a new vertex to those for any algorithm. So this proves the lower bound and proves that first fit is optimal on trees. Okay, stepping from trees to bipartite graphs, we have a very simple theorem. Beta kappa bipartite sits between kappa plus 1 and 2 kappa. We were not able to resolve this gap yet. The lower bound just comes from the class of trees, because bipartite trees are contained in bipartite graphs, and the upper bound is attained by CBIP, as we saw earlier. Surprisingly, when we take this small step from bipartite to three-colorable graphs, there's a very sharp contrast. So even with a single connected component, beta 1 chi is infinity for every chi at least 3. So an adversary can force any algorithm to use arbitrarily many bins while producing just a three-colorable graph with a single connected component. So our strategy for proving this is for any algorithm A and any T and any integer T, the adversary constructs a three-colorable graph, G, so that the algorithm A uses at least T bins to color G. So the construction proceeds in layers, which we denote L1 to LT minus 1. So we first present all the vertices in L1, then all the vertices in L2, and so on. So we first present L1, then we present L2 connected to some vertices in L1, then we present L3. I'll get to the details in a minute. Connect to some vertices in L2 and so on. The goal is to show that for each I, that any algorithm uses at least I plus 1 distinct bins in the union of L1 up to Li. So in L1, it uses at least 2 bins, in L1 union L2, at least 3 bins, and so on. So let's see the details. Layer L1 is simply a path B of sufficiently large length L1, which we'll quantify later, presented left to right. There are two cases. So either the algorithm A uses T bins just inside layer L1, in which case we're already done, or it uses fewer than T bins in L1. And then by a straightforward application of the pigeonhole principle, we can show that there are 2 bins which are large. We're going to call them B1 and B2. By choosing non-consecutive vertices, we can get bins B1 prime, which is a subset of B1, and B2 prime subset of B2, each of size at least L1 over 10T. But these are non-consecutive. And then we use these to produce the layer L2. So layer L2 of size L2 is produced by attaching each arriving vertex to one vertex in B1 prime and one vertex in B2 prime. So we're forcing any algorithm to use some color that differs from the colors 1 and 2. Again, either the algorithm uses a bunch of different bins, in which case we're already done, we get T bins, or if the algorithm uses very few bins, then there is a sufficiently large bin B3 prime. You should be noticing a pattern here. This is inspired by arguments from Ramsey theory. And we can just repeat this argument. So we get the bin B3 prime, B4 prime, and so on. So the process terminates when the adversary presents a single vertex in the layer LT minus 1 and forces a Tth distinct color for any algorithm. So now we need to guarantee 2 things. The first thing we guarantee is that all sets are sufficiently large. So we have a system of linear inequalities, and we can show that the total number of nodes is some exponential function in T. The second thing we need to guarantee is that the resulting graph has chromatic number 3. But if we remove this path P from L1, then the remaining graph is just a forest and is 2-colorable. And because we ensured that all the vertices in B1 prime and B2 prime are non-adjacent, we can just give them all a third color and then color the remainder of the path with the 2 colors that we use for the forest. So this is 3-colorable. And now because we actually counted the number of vertices, we get this corollary in the original setting that the one component bounded adversary can construct a 3 colorable graph on n vertices so that any online coloring algorithm uses at least omega of log n over log n pairs. So this is a lower bound on the classical competitive ratio, but under the one component bounded adversary. Okay, so with that nice construction, we can actually modify that to get a whole bunch of lower bounds. We have that beta 1 d inductive is infinity for every d at least 2. This is straightforward because that graph is 2 inductive. We have beta 1 ck free is infinity. We can do this by insisting that the vertices in v1 prime and v2 prime are, instead of just being non-adjacent, they're at least k distance apart. Beta 1 planar is infinity. This takes a lot more work to show, so we're going to skip the details. Beta 1 tree with k is also infinity for every k at least 5. This is really interesting because it comes directly from planarity and an interesting application of another result. So a graph embedding is one outer planar if it is planar and all the vertices lie on the outer face. It's k outer planar if it's planar and there is some planar embedding so that if you remove the outer face, it's k minus 1 outer planar. So essentially there's a planar embedding which is like an onion with k layers. As you remove each layer, you get to the, you keep changing the outer face and there's only k different outer faces. Essentially, each vertex is distance at most k from the outer face in the sense of distance. Okay, and then we can apply this theorem of Bode-Lander. It says that the tree width of a k outer planar graph is at most 3k minus 1. And since our planar construction is 2 outer planar, it's just a forest with a path, it has tree width at most 5. So this tells us that for tree width 1 graphs, which are trees, beta 1 tree is finite. In fact, it's just kappa plus 1, which is 2. But beta 1 tree width 5 is infinite. So a natural question here is, where is the step from finite to infinite? We have more open problems. The big overarching open problem is to characterize the class of graphs for which the online chromatic number is less than infinity under the 1CB adversary. We know that bipartite graphs are contained within this class, but 3 colorable graphs are not. And then what is beta 1 tree with k for k in 2, 3, 4? And also we allow the adversary to use unlimited vertices. So if we reintroduce the parameter n, what can we get? That's another natural problem. And of course, we can also apply this kappa component bounded adversary to other online graph problems. That's the end of my talk. Thank you.